Good morning, good afternoon, and good evening to one and all present here. I am Sibsankar Palit, and today I'm going to present Team Life's work on the topic of molecules in interstellar medium. Basically, how did they all originate, and how they paved the pathway to the very root or base of life as we know it, prebiotic chemistry. So, first of all, I would like to thank my team members and also Nostal and Innova Space for helping out and giving the opportunity to present here. So let's begin. As we all know that our universe began some 13.7 billion years ago, and in this whole saga, where is the place of chemistry? Because if we see the human body, it's made up of the different elements in different proportion. So all of these elements, as we know, were formed during the star formation and the different stages of the star. And you can see in this whole saga of 13.7 billion years, first it began with the nucleosynthesis. If I bring the chemistry part in here, just within the first second to 20 minutes of the after the Big Bang, and then the recombination of the formation of atoms and then photons became free. And after 100 million years later from then, the first stars were formed, and in their core were formed the same elements and different stages of the stars or these or different events in the solar system. So different elements are formed that actually form up the whole of human body. So in a way, we can trace our elements of which we are made of back to stars, back to the whole saga of the universe. So that's the very beauty of what we are studying in this case. And as we can see very clearly here that the composition, the cosmic composition is around 5% matter, and the rest is dark matter and dark energy. And out of this whole cosmic composition of matter, 98% is just hydrogen and helium, and just 2% of that 5% of matter consists of the heavier elements or higher elements like carbon, nitrogen, oxygen that makes up mainly of the most of our bodies or life itself. So, despite its very low proportion in the whole of the universal cosmic composition, it still is capable enough to create this beautiful tapestry or this complexity we call as life. And then, if we just consider our Milky Way galaxy, then 10% of the molecules that or the matter, I must say, is in the interstellar medium, and the 90% is found in the stars or near the star region. So, of course, we can say that the role of molecules in astronomy is becoming so important that it would not be an exaggeration to refer it, or at least a sizable portion of this cosmos, as the molecular universe, as rightly put up at the IAU Symposium 280. Next, moving up, we know that the field of astrochemistry is a highly interdisciplinary field of human endeavor, from chemistry to physics to astronomy, astrophysics, biology, geology, and engineering, and means a multitude of fields when we consider studying a particular aspect or a particular question in astronomy. And as beautifully demonstrated in this model picture, as you can see here, the detection of the molecules itself requires so many things. From laboratory spectroscopy to radio astronomy to understand the molecular abundance or collisional coefficients to chemical modeling to chemical network understanding and reactivity. So from laboratory means simulation done in laboratory to theoretical modeling and computational study to astronomical data and its analysis, all of these three together means contributes to the detection of molecules. And if you consider the location of molecular detection, of course, it includes the interstellar medium, the circumstellar shells, pregalactic gas, protostellar disks, and the atmosphere of planets and stars, of course. Moving ahead, as we can see, the next question that should arise in our mind is how are these molecules formed and how do they attain such level or degree of complexity in space and different celestial bodies. There are three main processes that have been understood till date with regard to the molecular formation in space. In space, so gas phase chemistry is one. Only small molecules and not much complex molecules are formed due to this process, and there are reasons for it. I'll come to it later. And then grain surface chemistry, modeling of chemical reactions occurring in dust grains, and much theoretical modeling and understanding and proposed reactions are flawed, and much developments are required in the understanding of grain surface chemistry. And then ice chemistry, as you can see here, actually it's this ice chemistry is very special with regard to formation of complex compounds. And at low temperatures of molecular clouds, that is less than 20 K, reactions slow and are limited by diffusion, and thus the species um, are formed, and they are more complex in nature in the ice matrices, and more discussion will be done in the later slides. And then these molecules in space can also act as the tracers of physical conditions in space. Means understanding the particular physical conditions means or of a particular region in space, and then they also act as unique probes of molecular excitation mechanisms, radiative transfer, and kinematics of different molecules in space. Okay, and then moving on, the main part of this whole presentation, the molecules in interstellar medium, how it's means what's its origin, and also how it's related to origin of life. Let's look into it a bit. We very well know that this field of astrochemistry has not been too old. It's just been more than a century, you can say. It started in 1904 mainly with Hartmann's work, and then 1930 another remarkable work in this with regard to understanding molecular dust in space by Trumpler in 1930. But in this whole time period, if you just see this graph recently published in one of the works of astrochemistry, you can see this graph clearly that mentions that from 1940 onwards till 2020, and now the number has increased a bit. You can consider that around 250 molecules have been detected till date, and I'm very happy to put at this point that in the last 3 years itself, 40 molecules have been detected. So you can understand that there has been a tremendous amount of improvement in the instrumentation and our understanding, theoretical modeling, and also the laboratory experiments that we do in simulated conditions. So that's the reason, as I mentioned this, that more than 40 molecules are discovered just in the last 3 years itself. In this whole number of 250 molecules detected since the last century. Then moving on, as you can see, there are kind of myriad of molecules detected from diatomic molecules to triatomic to even molecules of more than 12 atoms and 13 atoms, and then the polyaromatic hydrides, and then you can consider fullerenes. It's a polyaromatic hydrocarbons to fullerenes. So all of this together makes up a kind of forest of molecules that have been detected till date in space, and there are more molecules yet to be discovered further. And then moving forward, now in this picture, as you can see, the different stages of the planetary disk formation to formation of molecules, and then formation of stars, is very befittingly put up. And actually, the different molecules are formed in these stages only of the um, the planetary system formation, and also um, they attain complexity in different stages of this planetary system formation, and then followed by uh, stellar outflow evolution. Basically, it starts with the diffuse interstellar medium to star formation to planetary systems, and then it goes on to form the stellar outflow evolution, and is based on the mass of the star. If it's average star, then it explodes, and if it's heavier or a bigger star, then of course it implodes. But eventually, the chemical matter gets spread in space, and eventually the cycle continues. So there is no starting point to it initially, but the cycle, it's the kind of cycle that goes on and on and on, and replenishes the chemical content of matter in our universe. Okay. And gas phase chemistry has already mentioned earlier that they are instrumental in formation of the simpler compounds or molecules, you may say. But what's the reason behind it? As properly mentioned in the slide, that basically due to very low densities in the interstellar medium and also high radiation fuels, this leads to photodissociation of the newer formed compounds, and thus the initially formed molecules cannot attain more complexity. They break up. And there are various processes to these, as properly mentioned in this beautiful reaction graphic, as you can see here. Radiative association to reverse reaction, three body reaction and reverse reaction, neutral exchanges, ion molecule reactions, recombination reaction, radiative recombination in atomic state, and also radiative association, dissociative recombination in molecular state, and also the negative ion reactions and condensation reaction. Uh, Following this, there are also surface reactions, heterogeneous catalysis, absorption, thermal desorption, UV ion or electron impact, and carbon insertion reaction, and dust grain aggregation. Basically, from number H to number J, as you can see on my screen, from here to here, this forms a part of the dust grain chemistry that also forms the molecules in space, but the predictions made by it are often flawed, and more developments are yet to be made in this regard. And as you can see, that the most important and form of chemistry that is responsible for formation of complex molecules that indeed includes the biomolecules that are also essential to life as we know it, is ice chemistry. And it's beautifully it can be beautifully explained through this simple diagram up here. You know that ice is not that a good conductor of radiation or heat. So you know that these molecules on the dust grain, first of all, they are very closer to each other, leading to the greater probability of reaction to take place, and thus the formation of newer molecules. Secondly, you know that this ice acts as a shield to the newly formed molecules. So photo-induced ionization and bond breaking are also efficient in ice matrices, as compared to the gas phase chemistry at lower interstellar temperatures, like in the interstellar medium. Some ions and radicals can survive long enough to participate in the chemical reaction. Also, there is not breakdown of the complex molecules, and thus these complex molecules only are later on delivered via meteorites to asteroids, and then meteorites to the celestial bodies, and maybe that may have led to the development of life through the um, panspermia hypothesis only, that the um, the transportation of this chemical precursors to life from outside the planet to a planet, and then with proper conditions in that planet, life may have started. So of course, this can be a probability. And then moving forward, as you know, that link between astrochemistry and origin of life that we wanted to establish. Of course, there is a deeper link, and there are two specific reasons to it, and one of them is presented in this slide. Miss, you all will agree, I believe, that Miss water and also organic molecules are essential to life as we know it. So, as per the study of the ancient zircons in Australia, means, that suggested that Earth didn't contain a continental crust uh, and was thus not a magmatic hell. It suggests that water was present on Earth 4.4 giga years ago. And so water problem is solved. But now, what's the point of the organic molecules? How did it come up? To understand this thing, there are two approaches followed. One is top-down approach, understanding the phylogenetic trees, but at times it becomes difficult. There is a negative point to it that due to lack of evidence, due to the destruction of evidence due to lava or other factors that may have taken place in the past. So we cannot go and understand deeper into this from a top-down approach only. So this led to the understanding of astrochemistry and prebiotic chemistry through a bottom-up approach from basic to more complexity, and thus this approach adds in to the better understanding of how organic molecules may have arrived on Earth, or maybe how initial molecules were formed, and it eventually leads the pathway to the origin of life as we know it. So that's here is the importance of astrochemistry and the inclusion of astrochemistry in this connection with the origin of life. And then, as you know it, that ice-phase chemistry mainly gives rise to various biomolecules from amino acids to nucleic bases to sugars and the derivatives, amphiphiles, and many more, which are essential to life as we know it. And then, in fact, one point is that 70 amino acids have been identified from the study of the primitive meteorites, the chemical composition of these primitive meteorites, whereas 20 out of them are only essential to life as we know it, right? So isn't that great? So similarly, several isomers and variants of nucleic acids and sugars used in terrestrial life genetic material are present in the meteorites. And it seems fair enough that chemistry is a universal process, and maybe wherever there is this chemical richness in terms of the dense clouds and the protoplanetary disk, of course, life may be present there under proper conditions, but as I already mentioned, that under proper conditions, this point is to be noted that life can only emerge when the conditions of the host planets are favorable enough in all aspects, and then only the chemical precursors can give rise to life as you know it. Okay, so that is an important point to consider. Now let's get a brief understanding of what has been the research in the last decade and what should be the way forward. In the last decade, there has been some important developments in the field of astrochemistry. The understanding of the formation of adenine and alanine has been done. From cyanomethanamine adenine and from ethanamine alanine, and you know that these are a kind of important discoveries with regard to a pair of prebiotic molecules that gives way to the formation of amino acids that are essential to life as we know it. So that's why it's very, very important. Then, you know, pH 3 doped basically we know that phosphorus is very important to life, but how did it enter Earth's environment? That is also a question. Basically, phosphorus of glycerol phosphate isomers. Its abiotic synthesis occurs in the pH 3 or phosphine doped interstellar analog ices of the CH3OH, CO2, and H2O upon exposure to energetic electrons as a proxy of secondary electrons generated by the penetration of galactic cosmic rays into the interstellar ice. at a temperature of as low as 10K. So this is a way to bypass the potential phosphorus thermodynamic or water obstacles of terrestrial-based scenarios, and thus abiotically within ice mantles condensed uh, uh, phosphoric esters can be formed in these on these interstellar grains at temperature as low as 10 K, and thus the identification of glycerol phosphate in these ice. Means here also ice chemistry comes into play. Means has played a very important role in the formation of these glycerol phosphates, and in this way only via meteorites maybe these phosphates, these complex molecules that were formed in due to this ice chemistry in interstellar medium may have been later on transported to planets like Earth, right? And under favorable conditions it gave rise to life. Because phosphorus of course is one of the most important components when we talk about life. Then another is left-handed universe. How is the origin of life is connected to homochirality? On Earth, whatever amino acids we find, all the unique feature is all are left-handed oriented. So, um, and mainly the sugars are right-handed oriented. So there is a special thing that this raises question in our mind that is actually homochirality generated in space, and is there a role of circularly polarized light in this aspect? So recently, the first chiral molecules, pair of molecules have been detected, like the propylene oxide. One is the S propylene oxide and the R propylene oxide. However, the handedness of the molecule that is actually detected remains to be known. But this is the first kind of molecule ever detected, and in this decade only the first kind of molecule, the chiral molecule has been detected, and that's a good thing that tremendous progress in this field has been made. And then, NH2OH as a prebiotic precursor of the of the primordial RNA world hypothesis, that RNA molecules were responsible for the storage of genetic information and the catalysis of biomolecular or biochemical reactions in the primitive cells before the advent of the proteins and DNA. So in this case, hydroxylamine means uh, that is NH2OH. Despite several attempts, it wasn't detected, but in this decade only, it got detected in the interstellar medium towards the crystal molecular cloud G plus 0693 to 0.027 located in the galactic center. And basically, the predictions made by the chemical models and the measurements during the laboratory experiments, it has been observed that the formation of hydroxylamine in the interstellar medium is via hydrogenation on the dust grain surfaces, with possibly contribution of again that ice chemistry comes in, as the ice mantle and then ammonia oxidation process. And also hydroxylamine is a central species in the synthesis of pyrimidine ribonucleides. It's a good thing that it got detected, and it has given us many insights into what could have happened in this formation, or maybe the how it could lead the pathway to the formation of other essential biomolecules that are important to life as we know it. So these are some of the discoveries or insights that we have received during this decade with regard to the field of astrochemistry. And then all of this that I have been discussing till now gets validated in this slide through the bibliometric output that we generated using many articles, more than 150 articles from the Voice Viewer, using the Voice Viewer software, and these all are indexed journal articles from Web of Science database to get a better understanding of this dense network. The dense network validates that this deeper connection exists, but to get a better view in this next slide, you can see here astrochemistry is connected to origin of life and origin of life to homochirality. So as we understand more about chiral molecules in space and try to relate it to homochirality and get proper evidence of whether homochirality has been generated in space or not, maybe someday when we generate this thing again, the future research should focus on this to bring the link, direct link between homochirality and astrochemistry. To understand whether there is a link between homochirality and astrochemistry, or it's just a false misconception that we have in our mind. So that future research will eventually unveil that, and let's see what the future holds for this kind of research. And then in this better view, you can see astrochemistry related to many aspects, and mainly I would like to point the this thing to the indirect connection it makes with glycine. Glycine is essential for our life, and it has been detected in the meteorites that we have on the Earth surface, that we have received and studied on the Earth surface. But unfortunately, till date, the region in space or interstellar medium most probably hasn't been detected or found out where glycine has been formed. So when we find it in meteorites, most means, it is very much sure. It's a sure thing that it has to be formed somewhere in space, means somewhere in the molecular clouds. But where? So that thing needs to be detected, and future research can surely take this into account. And then again, this is more of the deeper interconnection and the developing field that is coming up, like the computational chemistry in understanding gas-phase chemistry and eventually astrochemistry is going to play a great role. And eventually we have a speaker on this topic maybe day after tomorrow, most probably. So she'll be talking on and presenting on this new methods of computational chemistry or computational astrochemistry, how it's very, very beneficial to understand in a deeper way at this whole field of astrochemistry and understand molecules in a better way. So we will surely look into that. And then does all of this just leads to basic understanding or fundamental understanding like chemical evolution, chemical reactivity in space, and life, an origin of life connections? Not actually. It is pushing the frontiers of spectroscopy, remote sensing and observation, in situ sample collection analysis, spacecraft designing, and even laboratory and theoretical approaches. And also it has already influenced many fields like increasing the laboratory spectral sensitivity and also the acquisition rates applied to fundamental chemical problems. Then atmospheric chemistry, of course, it is very, very related. Application to the newer methods of theoretical and computational study. And then informatics and machine learning has also benefited from this progress in astrochemistry. And then applications to materials development and gas or surface chemical interactions can also be expected in future, based on translational study that we do in astrochemistry, where we translate the work there or the methods used there into other fields of human endeavor. So that's, of course, is pushing the frontiers, is pushing the boundaries and influencing many, many fields besides the fundamental or basic study that is mainly is the motive during astrochemistry research. So that's, of course, a good thing that we should consider. And this review work actually aimed to provide an overview of the different aspects related to molecules in space, and of course, focus on the molecules in interstellar medium and how it's related to origin of life on Earth and as well as other worlds. And basically, the bibliometric outlook befittingly shows the interconnectedness among different keywords of our interest, and also the potential connections and lacunas that should be considered for future research. And eventually, we can be very, very hopeful that in future, with respect to observation astrochemistry that is taking place and will take place in future in this era of wonderful platforms like ALMA, NOEMA, and JWST, where places uh, greater which places greater demands on laboratory astrochemistry on Earth as well, with regard to gas chemistry, gaseous chemistry, ice chemistry, and also green surface chemistry. So newer methods and approaches like computational chemistry will be adding in to this in a great way. And finally, I would like to end with a wonderful means, line by one of the authors of the literature we referred by AGGM Tillens in the Molecular Universe Review, and which was published in 2013, that Eddington lamented after the discovery of the first diatomic molecules that atoms are physics but molecules are chemistry. In contrast to Eddington, in many ways, I would say that with molecules, the universe is only now truly opening up. And of course, very befittingly put. And that's what is understanding of molecules is opening up to us a deeper understanding into the universe, a very strong tool chemistry after all is, and that will surely continue and will progress a lot in future. And lastly, we would like to thank Chandigarh University for access to Web of Science database, and also Mr. Shivajit Hajra for his valuable advice and also helping us with the bibliometric outlook. We would also like to thank Norcell's founder and chairman, Mr. Sohan Shita, and the whole organizing team of Norcell and St. Andrews University, the Center for Exoplanet Research, Scotland, for this wonderful conference and the opportunity that they have provided to us to be a part of this wonderful uh, uh, conference and meetup. And thank you very much, everyone. And do follow Team Life 2 and Beyond on different social media links. And thank you again for your patience. Now I'm open to questions. Thank you.